Hello. In this lecture, we're going to look at perception and fairness, especially in regards to AI solutions in games. So, this issue of fairness is something that comes up a lot in video games. Game players are easily frustrated if they don't perceive the game or some aspect of the game as being fair. And this often comes up when considering interactions with agents. So these agents will often be like enemies or opponents of some sort in the game. One classic example I guess, some dispute over fairness is the game Mario Kart. So the original and the successors all have a handicapping system built into the game. One aspect of this is the likelihood of collecting certain power-ups. So if you're well in the lead, you're going to probably only get inferior power-ups, and these augment your ability to race, like speed up or attack the other racers by throwing a shell at them or that sort of thing. So if you're in the lead, you're probably only going to get banana peels, which have limited utility in terms of gameplay. If you're further behind, though, you are likely to get power-ups that allow you to directly attack the players in front of you and cause them to wipe out or slow down, and then you get the opportunity to catch back up. So that is something that's fully in control of the game designers in terms of the rules implementation. But you can also have enemies that are perceived as being unfair. Maybe they are just too good, or in the case of perception, seem to be aware of more than they should be allowed. So in terms of fairness, you will often see disputes about fairness that arise from game design or the game rules. So that's something that the game designer has some pretty straightforward control over. But there's also issues related to agent ability and perception. Now, some aspects of agent ability are that have the potential to be easy to control. So, for instance, you can make an enemy move slower, and then the player can respond better according to the slower movement. Or you can reduce the frequency of attacks or the power, like how much damage the attacks do. But what's harder to adjust is perception, and this can be something that is especially frustrating in games, especially certain types of games. So, for instance, you might think of a game with stealth involved. So if you're going to have a game with stealth, then you're really putting a significant burden on the ability to design a realistic sort of perception for your characters. So we're going to look at some, at a high level, look at some aspects of perception in implementation. So just in relation to artificial intelligence, perception modeling is something that is fundamental to some domains, especially robotics. So you need to be able to get your robot to be aware of the environment. So maybe camera systems or LiDAR, sonar, other means of making measurements from the environment, and then from that being able to build a model of the world and perform some task. And so there's a lot of effort that needs to go into making functional robotics solutions. But in video games, the agent has access to all the information you might need already in the simulation, and is often already in a discretized, easy to work with form. So for instance, if you want to know where the player is, and meaning the game object that the player controls, well, that is a discrete entity typically, maybe like an object-oriented design. You've got a memory reference to all of the relevant information for the player controlled game object. That would include things like position, velocity, and so on. And if you recall from our discussion of agent movement, we know that that is really all you need to begin getting an agent moving towards the player. So this doesn't take into account any aspects of perception. We just immediately have access to this information. And so this can be problematic if the player is expecting the ability to hide, for instance. Just directly grabbing a memory address for the player position does not take that into account. So again, we have all of this information about game state. We can directly access it. In order to accurately model or pretend that the agent has perception, we're going to have to hold back some information. But that holding back, that's not necessarily something straightforward to do. We have to figure out, well, from the context that the agent currently has, what information should be available to it. So a lot of this will be based on like spatial relationships, and so this is where a lot of the complexity can come into play. So in terms of simple game design, you often will just have all of the agents just immediately aware of the player. You can think of something like Pac-Man. Now that's such a simple game that it's not really a detriment to the gameplay that all the ghosts know where Pac-Man is, and they can make decisions on how to move closer. So there's a bit of level design to simplify things, and the simple single screen world. So the ghosts can basically just move in the closest like up, down, or left, right direction towards Pac-Man, depending on what move is available, and they can get closer. Each ghost has some slightly unique behavior as well. But that is something that the player easily accepts, that all the ghosts will move. But if you had, let's say, a game like a first-person shooter that has an extensive level, you would not want all the enemy agents to immediately move towards the player. It would just overwhelm the player if you had every single enemy in the level move towards the player, especially if they had the means to get there effectively with, say, path planning. So you can control a little bit of expectation through some simple solutions, like just having deactivated agents until a certain moment, like the player comes into view, or perhaps a trigger zone is entered. So I have a simple depiction here showing where the player might walk into some zone. So just a simple geometric calculation to check if the player position is inside of a region. Once that occurs, that generates an event, and it either spawns or activates an enemy. And so you can have multiple of these sort of trigger type scenarios to bring new enemy encounters into play. So this is a very simple scripting sort of solution that kind of addresses this issue of perception and allows us to control, kind of schedule these encounters with enemies according to player progress. It also, of course, has the benefit of, let's say your game can only maintain an interactive and enjoyable frame rate. If, let's say, you have a maximum of 5 enemies on the screen at any given time. So this would be the sort of thing you might consider doing to sort of maintain that level of quality. But if you have, like, let's say, a stealth game, then you probably want to have enemies that are on screen that the player is interacting with to a degree, but that are not aware of the player don't indicate that they are aware. And so this sort of thing can be frustrating. Anytime you have like a more sophisticated gameplay, especially players are already familiar with games that have stealth elements to them. And if you have a game that has similar like 3D graphics, fidelity, and character movement, they might expect to be able to be stealthy in some way. And so there's some obvious sorts of cues that might lead to these expectations, such as the enemies, their visual presentation to the player. Maybe if they're humanoid, they have a head that can face different directions, maybe eyes in the front of their head, and so it's clear that there's like a backside that would be presumably undetectable. The player would not be able to be detected if the player is behind the character or the agent and not making, say, any sounds, or otherwise would be detectable. So if you just have a simple enemies always aware of where the player is when they have spawned in or they're active, that could be that could easily be frustrating and a source of this this feeling by the player that the game is not fair. So maybe this would be like an opportunity to model perception. We could consider, for instance, whether the player can or whether the agent can see the player, and figure out a way to model that. So again, just to recap, from a development perspective, it's easiest just to have your agent access whatever simulation state that they need for making their decisions. But that can easily introduce this notion of a lack of fairness in the game. And so because of that, we want to filter information according to these perceptual abilities. So the first simple solution we might consider is to have a limited sight range. And so this, we can just do a distance calculation. In fact, we could even use squared distance compared to a threshold. So squared distance between enemy and player, so that relative position vector. We can take the magnitude, squared magnitude of it, compare it to a whatever our threshold distance is squared, and then we can figure out whether the player can be seen just by the distance. And so this immediately we can get some improvement in gameplay, especially if we have larger open or more open sort of areas. But that's not going to fully enable our sort of stealth scenario that we've considered so far. So the next thing we might consider is maybe introducing an angle relative to the agent's head. So if we have say a 3D model for our character, the agent character, we know where the head is looking, and so that forward direction we can do a relative angle comparison. So we can calculate the angle from the enemy to the player relative to the forward direction of the agent, and if it's within a threshold, then we know that the player is within the limited sight cone. So we would perhaps have two tests. We would have one is the distance test. Is the player close enough to be seen? Furthermore, is the player near enough in terms of an angle to where the eyes are looking? And again, this is all modeled, but this will add a lot without a whole lot in terms of calculation. This will add a lot in terms of the ability to support this notion of perception, and then improve the perception of fairness by the human player. Next, we've got a scenario where we have a much more challenging sort of scenario, and that is where there might be an object. So the player could be within the distance that the agent can see. So the player is close enough that the AI agent can see them. Also, could be within the angle to be seen, so the forward direction of the head. But maybe there is an object in the way, say hidden around the corner of a building, or there's a rock, a big boulder that the player is hiding behind. So in this case, things get a bit more challenging. We need to check to see if the player is occluded. Simple thing we could do is just raycast from the enemy's head to wherever the player is. And if there is a hit against game objects like the big boulder or wall, then we will just decide that the player is hidden. Now, of course, this could be insufficient to really accurately make this determination. What if the player, for instance, is hiding behind a countertop, but they're standing up, so they're not squatting down, but they're only the lower half of the body is hidden. Well, if you do a single ray cast, depending on where you're aiming that ray cast, it might hit the countertop, but in reality, the player should be in view. So this can cause some strange behavior. So solutions would be, well, you could add more ray casts, maybe cast a ray at the player's head, maybe at their torso, maybe at their feet, depending on the gameplay. Of course, the more ray casts you add, the more computational resources that you are going to take up. You might consider a more elaborate sort of solution. It is theoretically possible that you could actually perform some sort of rendering from the enemy perspective. And if you were to do so, you might use an approach of using simplified geometry. And this would possibly be available from the physics simulation that's already taking place. Generally, with physics simulation, you have geometry that is similar to what you see visually, but much more coarse in terms of how it describes the environment. So maybe say a wall with some intricate visual pattern on it would just be approximated with a large flat surface. The characters, like the player, may be approximated with a vertically oriented capsule collider rather than all the intricacies of the character mesh. And you can have this sort of simplified geometry for much of the physics simulation. But what you might do in terms of like a lower resource cost is perform a rendering using that simple physics geometry, and you would be rendering from the perspective of the player. Again, this is all off screen. Nothing is seen from the game player is not seeing this. This is just to facilitate the occlusion check. But you perform this rendering, and so like everything could be just white that's being rendered except for one object, and that being the player. Maybe you'd render it and say like bright red. And so if any bright red pixels show up on the screen when everything's done rendering from that perspective, then you know that the player is not fully hidden. And you might have it based on some ratio, like if there's more than 5 red pixels on the screen, that means the player's not well hidden, and then that could be the trigger. But of course, this is much more computationally expensive if you're going to use this rasterization rendering approach to do so. So it's clearly a challenge to deal with. Most likely, you would be using Raycast. One other thing that you might do is have not shown on the slide here, is you might have some pre-computed hiding spots. So that you, maybe if the player is in a hiding spot, maybe they have to be crouched for the state to count as hiding, and then maybe if the enemy is in some known discretized space, then they just simply can't see. So that way you might be able to do some sort of caching without having to make like runtime calculations. You could have this all baked, but it would I think limit what you're doing in terms of gameplay or in level design would be restricted. Now, another issue that comes into play, especially with stealth-based games, is attention. So, an agent, let's say that's like a guard in a stealth game, and you often see this in commercial games that have the sort of stealth genre gameplay, is that they might have sort of a neutral state. They're perhaps on duty, but they're not highly engaged. They're bored. All they're doing is serving as a lookout, maybe going on a patrol, but otherwise they're not expecting anything. They're not reacting to the player. And so if they become aware of the player or something the player has done or some undesirable thing, like they hear gunshots or the alarm goes off, then they enter a heightened state of alertness or attention. And in this point, as you might expect in real life, similar scenarios, is that if someone is aware of a problem, their perception is probably going to be amplified. They're going to really focus on the environment around them, find anything out of place, be able to more easily detect that there are intruders. And so this can work well in gameplay. And so as soon as, say, an enemy agent is aware of something like they find a dead body or they actually see the player, then their attention level can change. So even if the player runs away and hides, that attention level can stay higher. And we could model this change in attention simply by attenuating. Let me go back some slides here. Say our limited sight cone angle. Well, we could maybe increase the angle of the cone, or the sight radius could increase. And so some of the other perception type things that we might consider, we could also just change the thresholds according to this change in attention. And then maybe over time, for the purpose of gameplay, we'll dial back down attention. So the enemy agents might be at a high level of alert or attentiveness to their environment, and then eventually they say, oh, well, I guess the intruder has left, and they kind of go back to what they were doing before. So you can hopefully see how you might be able to model that simply by adjusting these coefficients on these tests we've talked about so far. We could improve upon our visual perception, and this would also be something that fits well with attention, is to have foveal and peripheral vision. So foveal is just like your center vision. That's like if you in real life, if you aim your head and your eyes at a target, well, you can scrutinize the details of whatever you're looking at, but things in the side vision you often aren't fully aware of unless something major happens. So your peripheral vision is very good at detecting motion, but it does not see details. So high contrast visual changes, your peripheral vision will pick up. Low contrast, slow movements, you might not even notice at all. especially depending on the context of where you're at. If there's other things moving around, like maybe uh, say trees with their branches swaying in the wind and leaves moving a little bit, then you might not notice someone sneaking around in the woods unless you were directly looking at them. And so this is something that can work well in stealth games and help with modeling. So um, so you can model this as simply an additional angle test, and maybe have it based on the character movement. So maybe if the player is within the peripheral zone but standing still, they don't get picked up. But if they're moving faster than a certain speed, they would get picked up. So you can introduce a bit of softness, I guess, to like a transition zone, as the player becomes more and more likely to be detected by the enemy based on this angle. Another important aspect of perception is the light level or the contrast detection of the agent. So in stealth games, you often will need a place to hide that doesn't involve full occlusion, like hiding behind an object. Instead, you might want to just be able to hide in the dark. So the classic game Thief had this ability, so you could hide in the shadows away from the lights that were around in the environment. And so you would, as a game player, you would look for these dark areas and hide in. And then there's also a little hint on the heads-up display that would tell you your light level. It's kind of like a traffic light. So if it was if you were fully in the dark, it would turn green. If you were partially in the dark, it would turn yellow. And then if you were out in the open, it would turn red. So that was because since you're playing in a first-person perspective, it was hard to tell how you might be illuminated. But the enemy agents would not be able to perceive if you were standing still in the dark. If you were partially in the dark and you had the yellow light, maybe the enemy agent would not be able to see you unless they got close enough or were looking directly at you. So this, as you might imagine, would be something that's challenging to compute. And so it's often the sort of thing where you pre-compute it. So as a game designer, developer, you might perform a baking process or pre-processing where the level is analyzed and you identify different regions through some sort of discretization, maybe breaking the world up into a grid or voxels, and then testing as if the player was occupying these different spaces. So if there was an object within these areas or volumes, you could do a calculation to determine whether there's, say, a line of sight from a point light source, and if it's close enough, according to the fall off of the brightness of the light with distance. And you could make a calculation and store in each of these zones or these discretized areas what is the illumination, and then that can be used for calculating whether the player is sufficiently in the dark. So this works well because many games already do a baking process, pre-calculating with a radiosity-based model for how light reflects in the environment, say off of walls or other surfaces relative to various light sources. So it generates a shadow map in the environment. Now the shadow map's only on surfaces, so in order to facilitate this pre-computing these hiding zones, there's additional steps that need to take place. But if you do this, then you can at least figure out where the player could be, where they would be, say, within a certain dark enough area. So the idea in gameplay is you have a cache of all of these different brightness values. The player will be occupying one or more of these areas, and you take the max illumination from what is stored in this database. And you take the maximum because you might have, say, most of the players hidden, but their head sticking out right into full illumination. So you would want to be able to account for that in terms of gameplay. Otherwise, things won't be very realistic. For camouflage, you might, in this case, rather than any sort of automated analysis, which I'm sure could be automated, but probably more likely you would have manually assigned values by designers. So, for instance, bushes or grass, tall grass, you might just have whole zones or areas that have been labeled by the designers that mark the type, and then the camo or camouflage potential of these different areas can just be done as a simple comparison. You know where the player is, what zone they're in, and then you might just say they're well hidden or not, or maybe it depends on the clothing they're wearing. So you just make the appropriate comparison with some Boolean logic. So you can support those sorts of situations. Now, in Millington's book, he describes an approach that he used in a game that involved a variety of different sensing abilities beyond just vision, also including hearing, but also smell, which I think is interesting. Not too many games have used smell, and those that have often have done it in a very constrained sort of way, where it really ends up being more like a visual, like you toggle a button and then you see a special visual display, and you see like these lingering smells, but it doesn't really account for like the propagation of how smells move around into actual detection. But in this game that Millington describes, at least the technology for, I don't believe it was ever released, but he has a sense graph, and it's used for all the different senses. So it's basically the same way that you might support path planning by discretizing the world. Millington describes breaking the world up into this finite element model of the game world. And then you have a graph that defines the connectivity between these different elements. And so you have different information that can pass through this graph. So you, in terms of gameplay, you determine, well, where are the different say agents and the player, but also objects that that can generate the sense information. So you could say have a sound generated at node A, which we could maybe think of as room A, as shown in this figure from Millington's book. So you have a sound, say, generated there, and the player is in location C, which is like a hallway. So if a sound is generated in A, well, we can just parse this graph. The sound is emitted in A, and then it will traverse from A to B. But the act of traversing is going to attenuate the sound. That means the sound's going to get softer. And so we can have pre-computed distances according to the different rooms and connections. We know the distance, and we know how, based on our model of sound, how much the volume will drop. And then we do the same thing with that information from B to C. So once the sound reaches C, well, it's dropped off in volume a certain amount, and so we can use that information to make a determination. Similar things can be done with vision, except the traversal is immediate, and you would say model the attenuation differently, but according to you can see much further distances. So you would it'd be much more gradual sort of attenuation, and things like smells can will be unique in that whatever generated the smell maybe is no longer around, but that smell can linger. And according to our simulation update, not only will we have like an attenuation based on distance, but the sound will propagate, like expand and move out and then dissipate. So we can kind of support these different types of senses, primarily vision, sound, and in this case also smell. But this can be useful for more elaborate sorts of gameplay with agents that engage in different types of senses. And this is also fairly performant. It rather than more elaborate sort of modeling that would be computationally intensive, this can work pretty well. One nice thing, like from a for the vision aspect of this, is you can imagine that, like if we were using the raycasting solution that we talked about before, you could quickly be overwhelmed in your raycasting if you're comparing against all game objects in the world or all geometry in the world. But by generating this graph, if we know where, like through a pre-computing process, what can be seen from where. So if let's say there is a room D not shown on this figure, that room A cannot see. So maybe the room directly on the other, like the north wall of room A cannot see D at all. So if the player is in A and the agent is in D, even though the player generates a sight event, the agent will never see it because the propagation of vision is based on line of sight. Hearing, however, it is possible for a really loud sound in A would maybe propagate and bounce around from node A to B to C, and then C could propagate on to D. So let's say a loud explosion or knocking over a bookcase. We could have that potentially be within the perception range of the agent. So this allows us to sort of limit the propagation of events that each agent would maybe need to have processing of. So we're limiting the amount of computation that's necessary for what's going on. I mentioned hearing already in the context of the sensory network concept, but one important thing in terms of gameplay with hearing is that we don't really want to model like the actual sounds being generated and process that signal to determine if the agent can hear it or not. So we think a little bit about the importance of hearing to a human. So outside of speech communication, what do we use hearing for? Well, they're really probably the most important aspect of hearing is that it brings attention to the listener about events that are maybe useful, especially from like a survival context. So you might imagine cavemen from long ago, lots of dangerous things in the world. If you want to hear the tiger sneaking up on you, it's probably important to be able to hear a twig snap in the woods. And then from that doesn't tell you a lot of information. We really need that visual sense. But what hearing is good at doing is we're able to figure out where the sound came from pretty effectively, at least on a coarse level, like maybe within 10 degrees. So we hear a sound, we can we turn our head, and then we can take a look at, well, what's there? Is it a tiger, or is it just a bird, squirrel, something like that? So we can quickly make that sort of determination. And so the things that we respond to are very short duration events, again, outside of communication. Um, so we're really not interested in doing some sort of elaborate processing of everything everything that is heard. Instead, we're just interested in the what creates these different events. And well, it turns out in gameplay, in software engineering, well, you can have an event system, and that this is common in games for things that generate sounds. In many cases, you'll have an event system generating software events, and then there's an audio engine that interprets these events and will play the appropriate sound. Might do other things as well, like generate a visual effect like a particle system, maybe a little cloud of dust. Say there's an impact. An event is generated on the impact from the physics simulation. Your software engineering for the game leads to an event generated that plays a sound of the impact. Also, anything else that is important for the game experience. But then the agents can, like the enemy agents, can listen for those events. And the events, it's not the actual audio, of course. It's the message that describes the need for the audio. And then that is what can be interpreted. So that's a discrete thing. The agent can consume this event, and maybe there's information in the event message that can be interpreted, like what sound it is, the position in the world. You can make a distance determination from that to decide, all right, based on the distance and the type of sound, maybe also the amount of energy it hit with, you perhaps have some attenuation factors for the sound. So for instance, in 3D sound engines, you have roll-off factors, so a near and far distance. And this is used for interpolating the attenuation. And so the sound card can interpret that as, well, what's the appropriate volume to play the sound at? And that same information can be, of course, valuable and easily interpretable by the agent without doing any sort of direct sound signal processing. Now, that said, you might want to do some pre-processing of sounds, could be useful. Human hearing, at least, and I imagine most animals, they do not hear all frequencies at the same intensity. So this is the perception of loudness, or volume of the sound. So, for instance, extremely low frequencies or extremely high frequencies, humans don't hear especially well, if they can hear them at all. But right around the sweet spot, they hear quite well. So you might actually perform a signal processing analysis of sounds to determine, well, how likely these are to be heard, maybe from a set of sounds in a sound bank. So maybe you have like footsteps, twigs breaking, gunshots, and so on. And how sensitive would a human be? And this could then be used to generate pre-computed thresholds for how likely the agent is to notice something. And then you come up with a function that takes into account the distance, the attenuation that would occur according to these distances, and what the sound was through this analysis. But this could also easily be done by hand too. You could just say, "Oh, I'm going to label this sound as highly attentive sort of sound, and these as more easy to miss," and then the agent will just make these threshold determinations through a little simple table lookup. So again, with hearing, you're not actually doing signal processing of the sounds. You just look at the game events that occur that generate the sounds, and that's what is interpreted for the purpose of modeling perception of hearing. Next up, we'll look at projectile projectiles and fairness. So we're thinking in the context of agents that like shoot things at the player. And so this is easily an area where you can do too good of a job. So we've already seen the calculations for aiming, and of course we can have highly effective calculations that are predictive based on extrapolating expected movement of the target, say the player moving, and we can really have an agent implemented that's a perfect shot and does a great job of hitting the player well beyond any sort of human ability. So we might be interested because of that, because of the impact on fairness being beyond human ability. We might want to introduce aiming error, model aiming error to make it more human-like. We might consider the actual aiming action, especially related to the amount of time it takes the player to, the amount of time it takes the agent to aim a weapon, and also reaction time that is an important factor in both the aiming error and the aiming action. So one way that we might think about this modeling human error is to consider the typical sort of distribution of some activity, like shooting a gun at a bullseye over and over. Well, this turns out to be a Gaussian or a normal distribution. It'll vary from person to person, but it will you'll tend to have a an average point that the user will hit. It'll either be right on the bullseye or offset, like a fixed offset from the bullseye, but then there'll be an error distribution around that average point, defined by a standard deviation. And so that would be a good way probably to model the aiming ability of an agent. We could just model a Gaussian distribution. So once we've determined where the exact target is that should be aimed at, we'll say, okay, we're going to back off of a perfect shot now. We figured out where the perfect shot is, assuming our prediction is correct, if this is a ballistic trajectory. Could be an instantaneous weapon, in which case, it's guaranteed to be a perfect shot in that case. So, very likely we will want to dial things back in terms of the agent's ability, just so that the player has a fighting chance. And so the way we could do this is say, all right, we want a distribution around the perfect shot according to a standard deviation that we will provide, and maybe determine what's appropriate empirically through testing what we want that to be. So we need some way to calculate a Gaussian distribution. I don't have the derivation of the distribution shown here, but it is expensive computation. So we're probably going to, for the purpose of real-time gameplay, we want an efficient implementation. So what I've shown here is a simple one, this Box-Moeller equation. That is the little block of code shown in the middle of the slide. And you can see the code here is pretty straightforward, though it does have some expensive operations involved. So we generate two random values, and then we need to calculate a log base 2 of one of the values and a sine of the other, and then take the square root of the product along with some other constants. And so once we do that, that allows us to generate this random Gaussian. And you can imagine it if we are doing this in a game that's a pretty expensive calculation. There is a faster algorithm not shown here, the Ziggurat. I'm not sure about the pronunciation there, but Ziggurat algorithm that has a few little little issues in terms of implementation, but sort of beyond the scope of this lecture. But if you're interested in the best possible real-time implementation, that's probably a more desirable approach. But another thing you can do is, if you're not really concerned about the being especially precise, and you really just want to have some randomness distributed around the correct value, then you might just simply use we've seen this approach before. I think Millington calls it a binomial distribution, but it's more like a fake binomial distribution, where you generate a random value minus another random value. And so the little snippet of code I show at the bottom of the screen here is how you could apply that to creating a random error distribution around a central point. So in this case, the mean, that would be the exact value plus standard deviation, which is not really a standard deviation, it's more like an error range in this case, times the first random minus the second random, all in parentheses. And so that'll give you something that looks more like a pyramid rather than a nice smooth Gaussian or normal distribution. One thing I wanted to mention about this is perhaps one of the cues that a cheat detection system looks for. So if you play any multiplayer games at all, you're probably familiar with cheat finding, especially those cheaters that are using an aimbot. And so one thing that you might look for, I'm guessing is probably nowadays implemented as like a machine learning thing, but a way that you would discriminate between an aimbot and a human would be perhaps looking at the accuracy of the shots, just one of many things that could be considered. And you, in fact, might do an analysis of the error distribution of shots over time. So if you're going to artificially generate noise, if you're doing something like the fake binomial of Millington, that's probably going to stand out compared to a Gaussian distribution. Similarly, if you had a Gaussian distribution that had such a tiny standard deviation that it was just not comparable to any human ever seen ever, then that would maybe be another trigger. There might be other types of analysis looking for the nature of how the random values are distributed, and could identify that you're using a pseudo-random number generator. Just hopefully no one's inspired to write software for the purpose of cheating in games, but just maybe something to be aware of. Could help inform the development of the actual effective cheat detection. So the next thing to consider is human-like aim movement. So there, in human-computer action, there is this law called Fitts' law, and this is based on studies of humans performing these aiming sorts of movements. And they initially started, it was in one dimension, turning a knob, I believe, and the knob moved a little visual indicator, kind of like on an old style radio. And you'd move the little visual indicator, like a little tiny arrow, along a line and try to land inside of a target region. And so the original studies would randomize the initial position of the arrow and the landing region distance and size relative to the little arrow that you're moving. And so this study found that the further away the arrow is from the target region resulted in the user or a participant in a study taking longer to move that position, even if they could speed up how fast they turn the knob or slow down. If they had this sort of dynamic control, it would still take them longer. And furthermore, the smaller the target area was, the longer it would take. So if you had say the arrow very far away from a very large target, that could be gotten to the terminating condition of the study for that trial very quickly. But if you had the arrow far away from a tiny target, it would take longer. And if you break down the sort of behavior that's taking place, the human strategy on average is to make a gross or a large movement to kind of get into the neighborhood, so that the individual would quickly move the arrow, but there'd be a lot of error because they're moving so fast. And then there would be a brief moment where they sort of stop the move and visually assess, well, what's the difference of the arrow position and the target? And then they'd make a refining move and another refining move. So you can kind of think of it as like in the game of golf. You hit, you hit with your driver, a very far distance, try to get as close to the pin or the hole as possible. And then you switch to a club that has more accuracy. And then you kind of go back and forth down to the point you're down to a putter, and you're always kind of cutting the distance down into a fraction of what it was before. Provided you're decent at what you're doing, and so that tends to be true of all. So the initial study was in that 1D with a dial. It tends to be true in all aiming sort of exercises. The coefficients might change, but the fundamental relationship between these terms tends to be pretty consistent. So if you're aiming a mouse, like 2D movements, trying to move a mouse cursor to a button, or changing an angle, the bigger the angle and the smaller the target zone leads to more time that it takes to do so. And again, that sort of large movements and then switching to progressively more refinements. It might be something that's hard to see, like if you're moving a mouse cursor trying to land on a location, you'll have all of this done in probably a fraction of a second for many use cases, unless the button's super tiny. But this certainly can come into play for like moving an aiming reticle in a video game to try to aim and shoot shoot a target. So a human is, when they see an enemy like a first-person shooter, they're moving the joystick or their mouse to aim. They're going to have a big movement, and then they're going to have some refining movements. Now, this is all compounded by the fact that the targets tend to be moving. We are complicating the scenario, but you might use this notion of Fitts' law to inform what would be fair and appropriate sort of movement of your agent. So when they're aware of the target, maybe the human player, they're fighting, the agent's fighting against the player and needs to aim and shoot at the player. Maybe upon initially seeing the player, the movement of the gun will be initially a large movement. Either the agent is shooting and that there's error introduced from just the fact that the movement was not perfect. So the error distribution could be introduced as part of these different these iterative refinements will each have some error applied to what would be the perfect movement, some error that's maybe informed by Fitts' law. And you could tune this all such that the agent can dial in their aim about the same amount of time as a human, and maybe slightly tweak that for like an awesome human versus not so awesome human. So you could have a range of kind of tuning parameters for the amount of error this introduces this kind of refinement. And again, this might be the same sort of thing that cheat detection could detect. It looks for a lack or an absence of those sort of iterative refinement movements and the distribution of the error distribution of the aiming movements. One other thing that you might want to check out for a more elaborate sort of like aim movement and maybe other types of movement as well is GOMS, which it also comes from HCI research. This it stands for Goals, Operators, Methods, and Selections, but it is a predictive model for human interactions with artifacts. So it's a little bit more general than Fitts law. So maybe like if you're working with knobs and dials, or other sorts of activities. So it's designed to be predictive of human activity. But if you're trying to make an agent act human-like, you might perform sort of like a task analysis using GOMS, and then use that to model what you would expect to perform. It's probably getting a bit overkill to go that route, but perhaps something to look at. And lastly, reaction time. And we could tie reaction time into the sort of iterative aiming refinement in light of Fitts' law, by also coupling reaction time into the equation. And so you may be aware that humans can only respond to something they see visually after some period of time. And this is around 0.2 seconds for a visual stimulus if it's expected. Takes potentially a lot longer if it's totally unexpected to respond. Auditory stimulus, like hearing something, you can respond a little bit more quickly. That's why they use a starter pistol in races. It's the quickest response. So like if you're racing a car in a drag race, they have the lights that light up that tell you when you're allowed to go. And so there's detection to see if the car has moved forward too early. And that's based on what's expected the best human could possibly do. And so if the car moves, it's not based on when the light first turns green. It's a delay based on what's the expected best a human could ever conceivably do. So it's probably slightly less than 0.2 seconds. And that if you go more quickly than that, then that means that you're cheated basically. And so you will get a fault and it won't count for that case. So how does this relate to creating fair agents? Well, we might not want to have our agents respond too quickly to what they see. So let's say the player runs past a doorway. You might have an agent that can immediately recognize the player has gone by the doorway and get a shot off right away. So that would be not really realistic unless they were already engaged with the player. And even if so, probably chances of responding just wouldn't be likely based on reaction time. So you might want to model reaction time. So one thing you could do is just introduce a delay on any observation. So whether that's responding to like player position, presence and position, sounds, that sort of thing, you could maybe just have a circular buffer to delay estimates. So you sample as a simulation advances. You're sampling all of these important measurements, but the agent doesn't immediately get to respond to them. Instead, it has to wait until it's provided with the information from this delay buffer. And so it's always working with the information from the delay buffer. And so in terms of shooting, humans, they learn to account for the delays in their own sensory system. So they learn how to lead a target just through practice. Like if they're firing a weapon, they're leading a target not only based on the distance, the time that it takes for the projectile to reach the target, but they also learn how to deal with the delays in their own sensory system, and where they're aiming is based on, of course, this expected future position. We've talked about prediction before, and so we could actually use like the current velocity, current velocity of the target. Maybe introducing some error to say that there's an error in the estimation of velocity, not to have a perfect value. So you could consider how we're going to introduce error into various aspects of agent decision making for the purpose of being more realistic. But you could aim according to that, and so you always are assuming this like 0.2 second delay. But the agent is not always working with old data because they can make a prediction. So simple case is that you just use the current velocity and extrapolate by 0.2 seconds. And so that's what the agent works with. Again, possibly with some sort of error either to the velocity estimate or the amount of time, future time prediction, something like that. You might possibly also use a Kalman filter, which I'm not going to cover in any depth, but just at a high level, this is used in has been used in robotics and other types of sensing for predicting based on old or sensor measurements that might have error themselves. That could possibly be useful, and overall, this sort of delay might be overkill. You could certainly get reasonably realistic and fair behavior from an agent through adjusting other aspects of their perception. So how far can they see? How well did they aim? That might be sufficient for creating a realistic scenario. We're talking about a pretty small value here, this 0.2 seconds. And so the impact of that in terms of the game player's perception of fairness, they might not even realize that's the contributing factor. So you might be able to account for it in other ways and therefore simplify your implementation. All right, so that closes out our look at fairness, and in particular how modeling perception of our agent plays into fairness, or the perception of fairness in gameplay.